Hello, this is Mr. Stansbury. I'm going to take you through some of the problems on the 16D Part 1 assignment. First one we're going to take a look at here is number 1. When a coin's tossed 96 times, 54 heads were observed. A chi-squared goodness of fit test is to be conducted to determine if the coin is biased with a 5% level of significance. So, Part A, write down the hypothesis that should be considered. So, for A, really what we got to do for these here is we got to do our P1 and our P2. So P1 is going to be the population proportion of heads. Proportion of heads. And then P2 is going to be the population proportion of tails. Okay, so let's see, that's that. So with that, now we can write our HO and our H1, right? So our null hypothesis and alternate hypothesis. So null hypothesis is always going to be that everything's fine, nothing's biased, all that kind of good stuff. So that would be when P1 should equal 0.5 and P2 should equal 0.5 as well. So the alternate hypothesis would simply be P1 does not equal 0.5 and P2 does not equal 0.5 as well. Okay? So that's for part A. Part B, how many tails were observed? So if we had 96 total times the coin was tossed, 54 of those were heads. That means, 42 were tails. Okay, so we've got 42. And then part C, calculate the expected frequencies of heads and tails, assuming the coin is fair. So I'm actually going to show you for part C here. I'm going to show you how to do that by hand and by calculator. It's just kind of handy to see it by hand, because then you kind of get a little bit better understanding of what the whole chi-squared calculated piece is. So what we want to do for that is we're going to set up a little table. I'm going to stop here and do that ahead of time for us. Okay, so set up a little table here, the observed, the expected, and then over here where we come up with our chi-squared piece here is observed minus expected squared, and then we divide that answer by the expected amount. Okay, so heads observed were 54, tails observed were 42. What we would expect would be 96 divided by 2 would give us 48 for both. So we would expect, if it was completely perfect and fair and all that kind of good stuff, it would be, we'd expect to get 48 heads, 48 tails, because it should be exactly 50-50, right? So what we do here is observed minus expected, and then we square it, divided by the expected amount. So observed minus expected, in this case 54 minus 48 is 6. So we do 6 squared all over the expected, which is 48. And if we do that, and sorry I didn't give more room. Let me see if I can't fix this, make it a little easier to see. Yeah, it's a little better, hopefully. So we're going to take 6 squared, which we know is 36, divide that by 48, and we get 75. So we get 0.75. And if we do this one here, 42 minus 48 is -6. When we square -6, divide that by 48, that's still going to be 36 over 48, which is still going to be 0.75. Okay, and then what we do for our chi-squared piece here is we add these all up. So we get total, we get 0.75 plus 0.75 is going to be 1.5. Okay, and this here is the chi-squared calculated. Okay, now you can also do that on the graphing calculator by doing this. So what you do on the graphing calculator, once you get these, the observed and the expected, is you go into stat, and then we're going to push edit. And then what we're going to do is we're going to put our observed in list 1, 54 and 42, and the expected in list 2, 48 and 48. Okay? Then what we're going to do is we're going to do stat. We're going to go over to test, and then we're going to go down to chi-squared goodness of fit, which is down here a little bit. There it is, chi-squared GOF goodness of fit test. And here's what we do. We push enter. All the observed data is in list 1. All of the expected is in list 2. And then we want to know what the degrees of freedom is. So it actually asks us to do that in E. So let's actually do that here. Remember, degrees of freedom is simply the rows by columns. Rows minus 1 times columns minus 1. So there's, this thing is a 2 by 2. So that means we're going to go 2 minus 1 by 2 minus 1, which is 1 by 1. 1 times 1 gives us 1. So that's our degrees of freedom equals 1. And that is, this here is part E. Sorry. That is this little bubble here. That's our figuring out our degrees of freedom. Okay? Okay, so we got to put degrees of freedom as 1. And then we go down into calculate. We push enter. And there's our chi-squared value, just like we came up with over here, which probably, especially with something with as little data as this, chi-squared, probably just as easy or easier by hand than it would be on the calculator, but it's just kind of a nice way to check. Also, the nice part here is this also does part F for us, which says use technology to find the p-value, which we just did is 0.221, let's call it. So that's going to be F. P equals 0.221. Okay, and then G, is there enough evidence to conclude that the coin is biased? So part G, we'd have to have our rejection inequality, right? So it's reject, always the same thing, reject HO if our p-value is less than the, no, sorry, not the HO, but the significance level, which here is 5% level of significance, so that means our alpha equals 0.05. So if it's less than alpha. So in this case here, our p is 0.221. Is that less than 0.05? This is false. So we don't reject HO. That means we accept HO. So that means there is not enough evidence to support that the coin is biased. And it's kind of nice because G leads us right into, like, the wording in here helps us with the wording of our solution. So there is not enough evidence to conclude that the coin is biased. Okay? Okay. Okay, let's take a look now here at number 3. Brian owns a chocolate cafe, wants to start offering ice cream in addition to his chocolate menu items. He initially makes the same amount of chocolate, strawberry, vanilla, honeycomb, and chocolate chip ice cream, assuming that the flavors will be equally liked. The number of sales of each ice cream flavor are shown in the table alongside. Conduct a chi-square goodness of fit test with a 10% level of significance to determine whether Brian should change the amount of each ice cream flavor that he makes. So this is the number of sales, and that's the total here. Okay. So in order to do our chi-squared goodness of fit test, the first thing we got to do is we got to set up all of our probability values here. So step 1 is let's say let P1, we can even, let's just do this, P1 equal the, or be the population of chocolate sales. So we'll just do chocolate sales. P2 is strawberry sales. so forth and so on. P3, vanilla sales. P4 is going to be honeycomb. And then P5 is going to be our chocolate chip sales. Okay? So, with that, our HO will be, let me see, I should not put equals. HO would be that P1 is going to equal, let's see, there's 1, 2, 3, 4, 5 of these, right? So each one of those should be a fifth. So P1 will be a fifth. P2 will be a fifth. P3 will be a fifth. P probability of the fourth one, honey sales, would be a fifth. And the probability of chocolate chip sales would also be a fifth. That's our null hypothesis. Alternate hypothesis would be that all these same things with not equal to. Like this. And actually it should really just be at least one of these is off. And obviously if one of them's off, at least two of them have to be off. Okay? So at least one of those has to be significantly different than 1/5. Okay? So step 2 is our significance level. So our significance level is equal to 0.05, right? Oh no, 10%. 0.1 would be our significance level. Okay? Now, step 3 is going to be making our expected value table here with our, and then calculating our chi-squared business. Okay, so let's set that up. Okay, here's our table all set up here. We've got all the observed pieces here. Expected would be 205. Divide that by 5, and that should be our expected amount for each one. So we do 205 divided by 5, and that gives us that we should expect, if it's all fair and equal, that all of these should have 41. That's going to be everything evenly distributed. Okay, so if we do the observed minus the expected squared divided by the expected, we would simply do 54 minus 41, which is 13 squared divided by 41, and that'll give us our value there. Over here we do 48 minus 41 is 7 squared over 41. 35 minus 41 is actually negative 6 squared. Negative 6 squared over 41. And we can do all those there, calculate all of our individual pieces, and come up with a total. But on this one here, on the last one's probably pretty easy to do because we only got a couple to do, but this one we've got 5 to do, so I'm going to suggest that we do this on our graphing calculator instead. So we're going to go into stats, and we're going to edit, and we're going to edit our 2 lists. And I went ahead and put those in already, 54, 48, 35, 28, and 40. All that there. And then all the 41s over here. Once we get all that in, now we simply go to stat, and we're going to go over to chi-squared test for goodness of fit. So we go over, go down, till we get to chi-squared goodness of fit. There's chi-squared test. Here's the chi-squared goodness of fit test. We push enter. Observed is in list 1. Expected is in list 2. And then now our degrees of freedom. So remember, it's the rows. Degrees of freedom is rows minus 1 times columns minus 1. Okay? So, honestly, here's how I like to do this. When I go through and I do that, I simply take out row, like if I just go through and I kind of mentally cross off one row and one column, the number of pieces I have, number of cells I have left is my degrees of freedom. So that would be 1, 2, 3, 4. So this thing should equal 4. And if you look at it, rows, we have 1, 2, 3, 4, 5. So that's going to be 5 minus 1. Number of columns is 2. 2 minus 1. 5 minus 1 is 4. 2 minus 1 is 1, which gives us 4, which is exactly what we just did right there. Okay? So on our graphing calculator here, we put degrees of freedom. We put 4, enter, and go down to calculate. We hit the calculate button, and it's going to give us our chi-squared total, which is 10. Let's change back to blue. Sorry. Let's see. 10.34. Is that right? 10.34. And our p-value is 0.035. And then p equals 0.035, right? So to go back to our 6 steps here, step 3 is our chi-squared total right there, right? Step 4 is officially our degrees of freedom here. And then step 5 is our plugging into our rejection inequality, right? So reject HO if, and it's always going to be if the p-value is less than the, let's see, our significance level, right? So our p-value in this case is 0.035. Is that less than our, our significance level, which is 0.1? This is true. So therefore we reject HO and therefore accept H1, right? So that means that at least one of these is not equal to a fifth with a 10% significance level. So then we say step 6 here, that we have accepted H1. So basically the proportions of each ice cream flavor sold are not all the same at a 10% significance level. So basically Brian should change the amounts of each ice cream flavor that he makes. Obviously a little bit less honeycomb, probably a little bit more chocolate and strawberry, and then probably the vanilla and chocolate chip are pretty okay. All right. Okay, so wrote down proportions of each ice cream flavor are not all the same at a 10% significance level, so Brian should change the amounts of each ice cream that's made. Okay, that's all we have for the 16D Part 1 problems here. If you have any further questions, please feel free to ask in class. Thanks.